All right, the next quick lecture is on a concept called molecular polarity. Now, molecular polarity is looking at the holistic, the whole molecule view of it. There's also something called bond polarity. Are the bonds polar? The bond polars is looking at a case-by-case basis. So when I have a chemical bond, or I should say compound, bond polarity is looking at each of these bonds between the elements. Are they polar or are they nonpolar? Molecular polarity is looking at the entire molecule as being either polar or nonpolar. And there's two different ways of determining this. First, for bond polarity, it's pretty simple for the national exam. If it's a covalent bond, and again, to be a covalent bond, we are looking at two nonmetals that are bonding together. Okay, they form a covalent bond. They share electrons. And again, on your chem helper, if you look on your periodic table, again, if we draw in that staircase, any element to the right of the staircase is a nonmetal, along with the element hydrogen. So those are your nonmetals. So this unit specifically, or primarily with covalent compounds, are looking at those elements and them sharing electrons. A polar bond is when two different elements bond together. Hydrogen forms a bond with carbon. Hydrogen forms a bond with fluorine. These are polar bonds, because carbon and hydrogen have different electronegativity. If hydrogen is bonded to itself, if you have a nonmetal bonded to itself, this is the only way that you will have a nonpolar bond, nonpolar covalent bond in AP chemistry, because they will effectively have the same electronegativity, and therefore they pull in the electrons with equal strengths and is a nonpolar bond. So all other bonds, if the bond is between two different elements, it's a polar bond. Now, if there's a greater difference in electronegativity, the most electronegative atom is fluorine. So hydrogen and carbon are not as far separated on the periodic table as hydrogen and fluorine. The greater the difference in separation between the two elements in the periodic table, more than likely the greater the difference in electronegativity is. So carbon is a little bit more electronegative than hydrogen, so we would draw a little arrow. That little arrow is called a dipole, and we'll talk more about this in IMF lectures. So the arrow is pointing to the more electronegative atom, and the length of the arrow dictates the polarity of the bond. HF, there's a greater separation in the periodic table, so that arrow would be drawing longer, which means there's a greater polarity in that bond because there's a greater difference in electronegativities. Okay, so an example of this, if I turn so molecular polarity now is looking at the shape of the molecule. Since most of the molecules you're going to look at are going to be bonds between different elements, the bond polarity criteria is met. So for a molecule to be polar, it first must have polar bonds. Well, that's pretty much always going to be met because it's going to be between different elements. Okay, elements that are bonded to themselves, like nitrogen, hydrogen, oxygen, these are always nonpolar molecules because they're bonded to themselves. The bond is nonpolar, so the molecule must be nonpolar. So we're looking at usually molecules where there's more than one element present and they're bonded to different things. So now it comes down really to a question of shape. Is the shape symmetrical or asymmetrical, if you can remember back from honors chemistry? Well, okay. Now again, lastly, why is this important? Why is it important that if a molecule is polar or nonpolar? Polar molecules have a greater attraction or greater intermolecular forces for each other. And if they're held together by stronger intermolecular forces, this is going to have a big impact on its chemical and physical properties. And that's what next week we're going to focus on, or later in the week next week, is we're going to focus on how this affects their chemical properties. How do IMS affect properties? So polar molecules tend to have higher boiling points and melting points than nonpolar things because they are not as attracted to each other. Okay? And that is your lecture on polarity. Page here. There are two causes of asymmetry. What causes asymmetry? Now again, if a molecule is asymmetric, it is a polar molecule because the geometric shape of the molecule causes the dipoles not to cancel out. Okay? And if they don't cancel out, the overall molecule has a dipole and therefore has poles, a positive and negative pole, making it a polar molecule. So the first criteria, what causes asymmetry, is if the central atom has different things coming off of it. So here we see chlorine coming off, but all the others are hydrogens. This immediately is an asymmetric molecule and therefore is a polar molecule. It gets a little bit harder with the next one. Students often think that this is symmetric because we got 2 chlorines and 2 hydrogens. But the rule of thumb says if the atoms are not all the same, it is asymmetric. Why? Well, if I were to actually draw the VSEPR structure of this molecule, the hydrogens are not actually directly across from each other. Neither are the chlorines. And now if we look at the polarity of each of the bonds, chlorine is more electronegative than the carbon, but the hydrogen is less electronegative than the carbon. So if I look at all these arrows and do vector addition on them, they will not cancel each other out, okay? You'll notice that for all of these, if I kind of draw a arrow, where do I predict all these arrows that kind of summate through? They're probably going to summate through between these 2 guys right here. And that is called the resultant vector. This molecule has a leftover resultant vector. All these arrows add up, pointing probably in this direction, which means this ends up being the negative end of the molecule, and this becomes the positive end of the molecule. The molecule is polar. So keep it simple. If the atoms coming off are not all the same, then it's asymmetric. One little exception to that is something like C2H4. And that is the polar bonds are these guys right here. But this guy is not a polar bond. So when we're looking at symmetry arguments, we are not effectively looking at nonpolar bonds. We're looking at just polar bonds. So again, if I were to draw the VSEPR geometric shape of this molecule, this is what the molecule looks like. And you'll notice that these 2 arrows actually point head on to each other, and so do these. And therefore, these guys will end up killing each other, and therefore there's no overall dipole left, and that molecule would be nonpolar. So this is a symmetric shape and is a nonpolar molecule. The rule of thumb with hydrocarbons is if all you have is carbons and hydrogens in the molecule, it is symmetric because the hydrogens will be across from each other in a different carbon atom. Okay? So are the atoms coming off, yes or no? Second criteria, another way we can have asymmetry is if there's lone pairs of electrons on the central atom. Water is polar because it has lone pairs. Doesn't matter how many. If it has 1 lone pair, it is polar. This is a polar molecule because it's an asymmetric shape. Ammonia is polar because it has lone pairs. Okay? Asymmetric shape. How about BH3? Is BH3 polar? Students think it's polar because it's got 3 atoms. 3 is odd, so if it's odd, it has to be polar. But if we look at the 2 criteria, the atoms coming off are all the same, and there are no lone pairs in the central atom. This is a symmetric shape, and this is a nonpolar molecule. Okay, so that's how we figure out polarity. So now what you need to do is go back to your tables and look at the geometric shape of the molecule, and if it's symmetric, you're going to put down nonpolar. If it's asymmetric, you're going to put down polar. Right here's an example of a test question, a multiple choice question on the national exam. Real quickly, pause the lecture and arrange these 3 bonds in order from least polar to most polar. Go ahead and do that, please. What we're looking for here in this is the difference in their spacing on the periodic table. While oxygen and fluorine are the most electronegative atoms, they are the closest in electronegativity, and therefore this bond would be the least polar. NF is separated next, and SEF has got the greatest separation on the periodic table, and because of that, it is got the greatest polarity because there's the greatest difference in electronegativity. So this is how we would do a multiple choice question on bond polarity. The greater they're separated on the periodic table, the more polar that bond is.